I'm live. Good morning, everybody. Welcome to another Celestial Navigation Live Lectures, Part 2. The video of yesterday is available on my channel. I will give everybody a moment to confirm you are here in the chat box on your starboard side, your right side. And we will start with today's lecture. If you can hear me, blink twice. Blink. I have all the tools, everything is ready, book is here, paper is here. Good morning. Good morning, Ivan. Let's see. Do we get anybody else? If we don't, we're going to start with the lecture. So, drž figa. Evo, taman 10 sekundi prije nego što ću krenuti sa live streamom zvala me jedna gospođa, ima stan na Šubićevcu i za najam, pa možda napokon riješim svoje stambeno pitanje nakon 39 godina, tako da cross fingers. Bokic Stipe. Predavanje će biti na engleskom, mora biti na engleskom. Ako se ova dvojica koja trebaju slušati ne preključe, ali će biti na engleskom ipak radi njih jer moram se čuvati video. Ok. We shall start. Yes, thank you Ivan. Thank you Ivan. I'm so like, I've never in my life lived in the apartment that has living room. It's always bedroom, toilet, kitchen. That was it. So if this actually is... I'm so excited. I mean, for the first time in my life. I'm going to have a living room. I think I'm going to take 1,000 pictures of just a ridiculous living room. Can you imagine to have a living room? So crazy. Okay. Ivan is here, Stipe is here. You both understand English. As I said, this lecture is for my English students. They made a note yesterday that they might not be available today. Never mind. I told them that they can watch the video. So we will start. Yesterday, let's switch to the camera. And I'm going to also show you something interesting. Ivan, you already know about this because this happened in one of my live streams with you. Is what I'm going to do now. Like right now, I'm sitting behind my computer and I only have one microphone on. And what I'm going to do right now in 3, 2, 1 is right now I have my two microphones on. One is the main one in front of my computer, and the second one is, and I'm standing in front of it right now, is my camera that is recording this. Now, the sound that you hear right now is like echoing. I had one officer from the harbor office. He's also joining in on this as a secret admirer. He's always listening. He told me that he heard this echoing sound when he was listening to me, and that is due to two microphones being on at the same time. So right now I just turned my main microphone, but I'm sitting in front of my computer, so that means right now the microphone that is on is my microphone from this camera. And what I need you to confirm, just so it's okay, which one is better in general. So because right now I'm sitting, so right now I'm far away from my camera. Is this one better for both options? So when I'm here or when I'm standing in front of the camera, like this situation, or is this one better? So 3. So now I turned off my camera microphone and my main that is here in this direction is on. This is me speaking directly into it, and this is me speaking maybe half meter, 1 meter away. So if you can just tell me which one is better. Is this one better or this one? So this is microphone number 2. Second one is much better. So second one. So let's name this one. So this one is B. This microphone right now is B, and this is A. This is A, and this is A when I'm moving around in my space. Closer one is better. Main mic, okay. Okay. Stupid. I'm confused one. Closer one is better. Okay. I'll pick this one, and if this one is bad, just tell me to switch, because as you can see, it's like switching is 1 second between 1 and 2. So I know, Stipe, you said A, but I actually forgot which one is A. Thank you, Ivan. Yeah, you're the best supporter here. Okay, now let's start with the lecture. Yesterday we drew this funny doodle thing with colors, and it's called celestial sphere. If you are learning celestial navigation, this is the first step. This is the first thing that you need to understand in order to understand everything that you going to do in the future. But as you can see here from my Picasso drawing here, we need to take this to the next level. And the way to take this to the next level is by using, let's switch on my screen, by using this. So I believe this is quite clear. You are all grown people with basic elementary school, so you know about latitude and longitude. So if you go down the equator, it's south, and it's east or west. So, and I can change Earth to, where is it? So we can go here, and we have east and west. So east and west from the prime meridian, and north and south. So this is how we measure coordinates of the position of something on Earth. We have how far it is from the equator, that's latitude, and we have how far it is from prime meridian, Greenwich meridian, that's longitude, can be east or west. If it's east, it's measured as in equation as positive. If it's west, in the equation you put that value as negative. North is positive and south is negative. So that is how you plot the values of these numbers in the equation, and that is how the equation separates 26 north from 26 south. So the signs are important. So let's turn that off, and let's go to the second most important thing about celestial navigation, and that is celestial sphere. So this is what we actually draw yesterday. We have observer in the middle, and this here, the blue line here, and this level here is his horizon. So somewhere on his horizon he has north, east, south, west. Depending where he's facing, he can only see 180 degrees of objects. Everything that is back to him he can also see, but he needs to turn around. Everything that is under his horizon is invisible part of the celestial sphere. The point that is directly above the head of the observer is called zenith, and the opposite point to that is called nadir. And we have a star here, and this, or any celestial object, and the height is measured from the horizon level. So we have 0, and then it can go up to 90 degrees, and as you can see here, it doesn't go beyond 90, it's actually switching back to 80, 70, so it's on the other side, on the back of the observer. So let's go back here, and this is also azimuth or horizon coordinate system, because the two coordinates, in order to express the position of this star in this coordinate system, is by using azimuth, so bearing, and height from the horizon. So horizon is the main level, and main distance. So on this level, on this circle of 360 degrees, we measure angle, and angle is measured, as you can see, from 0, that is north, and it goes 90 degrees, 140, and this should be 180. So the south is exactly 180, and then west is 270 all around, and the height is this one here. So this is what we actually draw when we are drawing celestial sphere. We make our horizon level, we find azimuth on that line, and then we connect zenith and nadir. And on that height circle, so this is called height circle, we split this section from here to here into 9 identical parts, and then depending on the height measured, we plot a star or object that we measured. So that would be the first part of celestial sphere. Now this diagram I'm using, so this sphere I'm using, this is instructional sphere, so this is not some private program, this is actually an open program that you can download and use so to practice. And also see, you can have marking for zenith, nadir, horizon plane, meridian, so you can have labels what is what. And also I'm moving this with my mouse. You can also do the same by gliding or sliding the slider here, and also you can type the value here. So this is one way of getting your celestial sphere faster when you are drawing it. You can also do it here and check are the numbers correct, but this is something that if you are in high school, if you are in maritime college and part of your exam is drawing celestial sphere, this is what you can use for practice before you actually start drawing, to get approximate value, approximate appearance of the sphere. And as you can see, you can move around, you can turn the globe sideways, you can put it east in this side and west on this side, so everything is adjustable. Another thing that we have here is this one. Where is it? This one here. So this one is slightly different. As you can see now here, this is my horizon level, and if I want to measure the height, it will be from here to here. But this simulator is not showing that. Now we have the equator line here and declination line here. Declination circle is connecting celestial north and celestial south. Hi Matthew. I'm just explaining these demonstrators, these live spheres that you can use for practice when you are drawing celestial sphere. And this value here that you see right now is declination. So if we go back on this one, here you see as I move star up and down, I have positive and negative, and the level that is 0 is actually horizon, because this is azimuth and altitude demonstrator. So altitude as a height and azimuth or bearing from the north is here. So that is this part of the sphere. So this is horizon coordinate system. Horizon coordinate system is using horizon as the main level. You measure angle on that level, and you measure angle from the horizon towards the object. And then we have this one. This one is equator coordinate system, and this one is not measuring the distance of the object from the horizon level, but from the equator line. The angle here, so this angle here between the horizon and this equator line, so this angle here is actually your latitude. This here is your latitude. So that is how you get the equator line when you are drawing celestial sphere. You have your horizon line, and then the angle here or here, depending are you north or south. In this case, it is actually north. So it's 41 degrees north. So that means I put a dot here and I cross it, and at 90 degrees to that, I have the equator line. And this angle here that you see 20 degrees is actually declination. So that is declination of celestial object. It can be also positive or negative. So object can be north or south from the equator. The reason why I want to show you this using this simulator is sometimes people ask me, how can I see a star that has south declination and I'm on north hemisphere? Just because you are on north hemisphere, that it's not directly connected with the declination of the star itself. So just because you are here, this is the north hemisphere, you can clearly see that because of the angle between you and the equator, you can still see an object all the way up to, and look, your latitude is 41 degrees north. So let's see how far we can see an object. So we can see the object that is on our meridian. So this is our meridian here, meridian, our position. We can see all the way up to 50 degrees south. If our meridian was here, or if the star was here far away from us, it would be substantially smaller. So the bearing is also important. How far is the star from the equator, and we will still be able to see it. But just note that just because you are on north hemisphere, you see you are on north hemisphere, you are 41 degrees northwise, that doesn't mean that the only stars that are visible to you are stars that have positive or north declination. So you can see both of them. The only star that you cannot see, so let's say we have Polaris that is around here. So Polaris star is directly above the North Pole. So for this one, if we reduce latitude, I can do it like this with the slider. If I reduce latitude, I cannot see it anymore. So the Polaris star is a star that is mostly visible for people on north hemisphere, only on north hemisphere. People on south hemisphere cannot see it. Every other star rotates, so you have a certain section of stars that you can see, or constellations that you can see during winter, and you see them here on north, and then when it's summer you do not see them because now the people on south hemisphere can see them. So the sky switches places, except for those stars that are directly above north pole or directly above south pole. They are only visible throughout the year, all the time, for people on that same hemisphere. Now one more reason I want to show you this is there is something interesting here, and this is how they decided to put it. I actually have my plan, and I have a programmer that is working with me right now to make this simulator, but for me, for my site, for my page. And although this is great, I still miss some things that are very important to me as educator. For example, this value here, it says sidereal time, sidereal hour, and this is also an hour angle. And the reason why I want to be able to change it is, as you can see here, as I move an object left or right, it shows me a value of this in time. I need this to also be represented in angle as well. So I want to be able to click here to switch between time and degree, because basically what we are doing in calculation is we have a degree and we're turning degree into hour. So as I said yesterday, 1 hour is equal to 15 degrees. So that would mean this star here, 4 hours, 4 times 15 is what? 60? So this would be 60 degrees. So that would be the actual value that we would use in when we are drawing our sphere. We do not have time, we have an angle. So it's our angle, and it can be converted into time and back to angle by multiplying with 50 or dividing by 50. So this is 60 degrees here, and it goes all the way up to 360. 360 divided by 24 is 15 degrees. So every hour is 15 degrees. So 15 degrees, 15 degrees, 15 degrees, 15 degrees. Now this value here for each star, so this value 26 degrees, and this value but expressed in degrees is something that is fixed. It doesn't depend on us. You see what happens. So this is a star here. Look what happens if I change my latitude. Do you see? So these two values do not change depending on my position. So my position is not influencing these two coordinates for this celestial object in moment of time. So if I take a picture of a sky at a certain moment, this is how far this object is from the equator, and this is how far it is from the Greenwich meridian, so prime meridian, expressed in angles, but it can also be in hours. And if I change my latitude, you see, no matter where I am, these two values are the same. And because of that, these two values are printed in almanac because they do not depend on me. But what is important here is that this value here is from Greenwich. I also have my longitude measured from Greenwich. So this here is actually equatorial coordinate system. Equatorial coordinate system. It has two coordinates. It has this one, declination, and has this one. This is sidereal hour angle or hour angle from prime meridian, depending which one you are using as a 0. But if I want to change this, if I want to turn this into local equatorial coordinate system, the value that I would need is this value here from the blue line. Blue line represents my meridian, and my meridian is my longitude from Greenwich. So actually the angle in local equatorial coordinate system for this star would be angle from the blue line towards the star. So this angle here. And the way I would get this angle is by subtracting the angle I took from almanac with my longitude. So if my longitude is east, I would add it. If my longitude was west, I would subtract it. And that would turn this coordinate system into local equatorial coordinate system. Now, see, and once again we have negative declination. Sorry. I'm going to sneeze, sorry. So this is what we actually drawn yesterday. We draw celestial sphere by using this value. So when we are drawing celestial sphere, we need to have two coordinates of one coordinate system. So here either this one, so our angle and declination, so that's option number 1, or we can have height and angle on the horizon. And once we plot this, then we combine this image with this image, and we get one coordinate system and one celestial sphere. As I said, if you want me to send you this or link to this so you can play around, you can check the numbers, I can send you this. Just send me an email, I will send you the link. This is from university in United States, and it's all the Adobe Flash Player supported, so you need to have Adobe Flash Player on your computer to be able to use this, to see this. In 2020 you could do this directly on your browser, but as you know, the browsers are no longer supporting Adobe Flash Player, so you cannot do this anymore directly on their website. You need to download and use it on your computer the same way I'm using it. Okay, so I hope this part is clear now. Let's go back to camera. Okay. And back to the camera now. And I believe, be careful with your audio now, because I'm now directly close to the camera, so maybe audio is much louder. Now, what do we have here? What do we have here on celestial sphere that is important to us? What we need to extract? Now, let's focus on the red. I want to say red, but it's not red. It's something between red and purple. This line here. So this line here is the line of our height, and I'm just going to copy it here. So I have a line that starts here from the horizon to zenith, and this is where I have the stars. So I'm going to draw a star here. Something happened with internet connection. Are you still with me? It says excellent connection, so blink twice if you can hear me. We got disconnected for like a microsecond or something. this is what I'm drawing right now. This is an exam question on the oral exam. So if you have celestial exam oral, this is one of the questions that good. Okay, my computer just blinked once. It disconnected for a second, but okay, let's continue. So this, what we are doing right now, is we are extracting what is important from this image. After we finish with this image, what is important is this spheric triangle here. And this is called celestial triangle. You only have one. In terrestrial navigation you have three, but here we have only one. We have this one. And we have, once again, from here to here we have 90 degrees. From horizon, now follow me, from horizon to star, so from here to here, is the height of the star. So what is the value of this angle here? So from here to zenith is 90 degrees. From here to star is height. So that means this side here, the value of this side is how much? 90 degrees minus height. So if from here to here is 90, from here to here is height. No matter what the height is, the remaining, this side, is 90 degrees minus the value of height. Then we have the orange. Let's draw the orange. I'm going to draw the orange line a little bit bigger. So it's south. So where I'm going to draw it, it should be here. I'm going to draw it like this. The orange line. Now, the orange line goes from the equator towards the star. Here is small, so I draw it bigger. So I draw it bigger for you to be able to see. So from the equator to the star is declination. From the equator to the pole, North Pole in this case, is 90 degrees. So once again, equator to the star is declination. From the equator to the North Pole, celestial pole, is 90 degrees. So that means this side is 90 degrees minus declination. And we have one more connection. We have this one here. Between the equator, so the same equator that is here, so between the equator and the point that is directly above my head, so my meridian, and my latitude, so my position, in fact that's my position transferred into celestial sphere, this value here is latitude. Between the equator and pole north we have 90 degrees. So if between equator and here is latitude, that means from zenith to pole we have 90 degrees minus latitude. So those are the three sides of celestial triangle. We have declination here, and then we have the leftover of the declination, 90 minus declination. We have our latitude, and we have leftover from the equator to the pole, 90 degrees minus latitude. And we have our horizon, we have height of the object, and then we have a point directly above our head, and the leftover between the star and that point directly above our head is 90 degrees minus height. This zenith is a point directly above our head, so that means this level that we are using here is called our horizon level, and on this horizon we are actually measuring our bearing. So this angle here is actually bearing, it's our azimuth. And if we are using our compass with all the corrections, it's going to be azimuth true. The angle that is measured on the equator line, because if this is a pole and then we have a level here, the level of the equator, the angle that is measured here is local hour angle. This is how far the star is from our meridian. So this is a meridian of a star, and this is meridian of our position, the angle in between those two is local hour angle. And this angle here is angle P, and the reason why this angle is named P, because we do not need it, we do not use it. Now, why we do not need this angle here? Why this angle is not important? In order to solve something from a triangle, so let's say I want to solve this, or if I want to solve this, or if I want to solve this, what I need is to have this angle to be known. So follow me now. This is going to be pure mathematics. Let's say I need this side. This side is unknown to me, so I do not know the value of this side here. In order to get this side here, I need to have this value, and this value. So 1, 2, 3. In order to get this one, I need to have two sides and the angle that is opposite to the side I'm looking for. I do not need to know this or this. I just need to know the angle that is opposite to the side I'm looking for. So if I want to know the height, so I'm looking for a height, I need to know these two sides and the angle that is opposite to this side here. Now, in celestial navigation, when we are calculating values, this number is always known. How come it's always known? Because in celestial navigation, what we have is we have our true position. So this is our true position. And on this position, we measure height of an object, bearing of the object, time of the object. So that is what we have. We have time from our clock, we have bearing, azimuth, from our compass, and we have height that we obtained with sextant. And then we have assumed position. Assumed position can be anything on the globe, literally anything. You pick whatever you want, any number you want, and then in that case you have latitude that you will use. So you have this number from your head, you picked anything, and you use that number to get this height, and this bearing. And this bearing is going to be calculated. And then when you compare these two numbers, the actual one and calculated one, the error between those two values is the actual error between your assumed position and true position. So you would plot on the chart your assumed position, you would put bearing of the position that you get, and you plot the distance. Distance is going to be the difference between two heights, and that is how you get your true position. So this value here in celestial navigation is always known because we actually put any number here, because we say, okay, I imagine I'm here, and then you calculate the values that's supposed to be for that star if you are actually here. But you measure the value with sextant and compass from your true position. And the difference between the two numbers that you get, the actual number you measured and the actual number that's supposed to be if you are here looking at this star, is the angle and error in nautical miles. So that's the core of celestial navigation. So let's do this. So I'm not going to talk about this too much. If you want me to give you a lecture about sextant, how to use it and how to measure things with it, I'm going to do that separately, because that is not going to be in the exam itself. But this is sextant. This is what we use to measure angles. We have this blocking, you see, blocking mirrors in case we are measuring the height of the sun, so it doesn't blind us. We have reflective mirrors on both ends. We have this one here, and the first thing that you will notice here, that it goes beyond 90 degrees. The reason why it goes beyond 90 degrees, even though that everything that we measure is from 0 to 90, is that this device can be used like this to measure an object on the sky, or it can be used like this, and you have like lighthouse here, lighthouse here, lighthouse here. You measure horizontal angle between three lighthouses, and you will get your accurate position without need of calculating deviation and variation as you would have if you are using magnetic compass. So if you are using horizontal angles measuring like this, and the angle can be beyond 90 degrees, it can be up to 130 degrees. So you measure two angles between lighthouse 1, lighthouse 2 is one angle, lighthouse 2, lighthouse 3 second angle. You plot those two angles on the chart, and where they intersect, the circle where they intersect, that's your true position without any corrections needed to be applied. So you only have those two numbers. You have two angles measured with sextant. So sextant can be used like this, held like this, or like this. So those are two options. But if you want me to explain this in greater detail, what is this and how to use this, I will do that in the future lectures. But for now, let's focus on the calculations itself. I hope the triangle is clear, as much as it's possible to be clear. And let's now talk about three important things. Three important things when it comes to navigation is number one, time, second is azimuth, and third is height. So time, we need chronometer clock on our ship. Azimuth, we need to have precise compass on our ship that is calibrated, and height, we need to have sextant on our ship that is also calibrated and accurate. So let's now focus on the time. If the time is wrong, if the way we are measuring time or calculating time is wrong, then the entire equation, everything that we calculate, is going to be wrong. So let's start with Greenwich, and let's plot Croatia here. The time that we use in celestial navigation is not Greenwich time. It's not the time that is for this time zone. The time that we say UT time is not the time belonging to this zone. It's the time that belongs to this exact meridian, and that is important to know. So the UT time is not time belonging to everybody who lives in England. They are in time zone +1. So that is TX. X is time zone. So that is time zone for everybody living in England. That is not UT time. UT time is time specifically, exclusively for everybody on this meridian. Only on this meridian. Person who is east from this doesn't have this time, and person who is west from this, even by 1 degree, not just 15 degrees, it doesn't have this time. So that is important to understand the difference. TX time is the time that is shared by everybody who is in one time zone. So if this is 7.5 degrees east and this is 7.5 degrees west, everybody here is in time zone 0. So X is 0. So person who is here, living here, let's say has 12 o'clock. Here is 12 o'clock. Here is 12 o'clock. That is time X, zone time. So everybody who is here, they have the same zone time. But the UT time for person here and here is not the same. So if the UT time is 12 o'clock, person who is here doesn't have 12 o'clock, and person who is here doesn't have a 12 o'clock. And then we have Croatia. That is in X is +1. Once again, same thing. Person who is here has the same zone time, so TX of zone 1, and person who is here also have that same time. That is our economical time zone. But the difference between UT time and person here is actually their distance, this distance here, expressed in time. And for this person also, it is this, expressed in time. Now, distance between this position and Greenwich is what we call longitude. And let's call this person longitude Dubrovnik, like this, or longitude 2, because Dubrovnik is somewhere around here. And let's say this is Rijeka here. So this is longitude 1. And let's say the UT time is 12 o'clock. So exactly on Greenwich meridian, the time is 12 o'clock. So nobody else on the planet except people living exactly on Greenwich meridian have 12 o'clock. So how much is the time, the actual time, not TX time, the actual time for person living in Rijeka? And Rijeka is, let's say, 13 degrees east, and Dubrovnik is 18 degrees east. So how do I get the exact time for me here and for me if I was here? I need to divide 13 by 15, and I need to divide 18 by 15. So let's do that. That is how I express the angle in time. If I want to convert time into degree, I multiply with 15. If I want to convert degree into time, I divide by 15. So 13 degrees divided with 15 is 52 minutes, and 18 divided with 15 is 1 hour 12 minutes. So what that means is, if I read from the almanac, let's say if I read from the almanac, for example, that sunset is going to happen, so sunset is going to happen for a person on UT, so Greenwich meridian, at, let's say, 19 o'clock, so some celestial event, doesn't matter what, it's going to happen at 1900 for a person who is here. For me, that is going to happen 52 minutes prior, because I'm plus. So if it's going to happen here at 19, it's going to happen to me at 18:08. So when the time here is 18, I'm going to have, when the time on Greenwich UT is 18 hours and 8 minutes, that is when that event is going to happen to me. So if something happens on Greenwich, so UT at 19, to me, when that happens, so when I have 19, at that exact moment, Greenwich is going to be 18:08. So this is the data I take from almanac. This is when something is going to happen for person on Greenwich meridian. I convert that to my position. So it is going to happen at 19 o'clock for me, but when I have 19 o'clock, Greenwich time is actually 18:08. So when I have 19, Greenwich has 18. So for me, that event is going to happen at my 19 o'clock. For Greenwich, that would mean it is 18:08. Now, is this clear? This is very important. I will explain this in detail if this is not clear. If this is not clear, we cannot move on. Perfect. Okay, so one more time. We cannot have this number here. We cannot have this number, the number for us, because it will be too complicated to make book just for each individual meridian. What we have is, we have a book that tells you at what time something is going to happen for a person on Greenwich meridian. And then by knowing your longitude, so your longitude, the difference between these two, you convert that into UT time that is going to be at UT when you actually see that event. So you take your longitude divided by 15, and you do not round this up. So it is going to be 52 minutes prior the time that is mentioned on the UT, and that would be his time. So it will still be 19 for you, but at that exact moment, the UT time and the clock showing the UT time, that is your ship chronometer, is going to show 18:08. And why is this important? If you are on the west side, you can actually cheat and, let's say, forget and skip, because even if you calculate 19 and you are west from, you still have time. But if you calculate that you need to watch at something outside your bridge, you go outside and look, and the almanac tells you that you need to go outside at 19 o'clock, and you have a ship clock that is actually showing you UT time, and you read 19. By the time you go to see something at 19 o'clock on your chronometer clock, it's already going to be too late. It's going to be 1 hour too late, 52 minutes too late for your meridian, because this is the time that something is going to happen for a person on Greenwich meridian. For you, it is going to happen earlier. So you actually have to go outside when your chronometer is showing this time to see that celestial event. So if I want to calculate an event, time of event, I take UT time and I add or subtract my longitude, so longitude divided by 15, and I still get UT time, but this is UT time for me, for my event. If I want to get this time zone, the procedure, the formula is exactly the same, so plus minus longitude divided by 15. But in this case, once I divide longitude with 15, I round it to even number. So it needs to be plus 1, plus 2, plus 3. It cannot have minutes in time zone. So if, for example, I need to calculate what is going to be, if I have 12 o'clock here, at what time here, for this area, it's going to be 12. So I'm going to do that by dividing my 18 with 15 or 13 with 15, I will get 52, and I need to round that out to get the time zone. Then the time zone is plus 1 for both of these persons. The time zone is plus 1, so that means for both of them the time would be 13 on GPS. So this is time on GPS if the GPS is calibrated to the zone time. But if I'm looking at chronometer, I need to get the exact minute. I cannot just ignore the fact that I'm here this much away from the Greenwich, or I'm here this much away from the Greenwich. And this is something that people constantly confusing, because the formula makes two values as they are the same. But if you are calculating UT time for your meridian, you divide your longitude with 15 and you do not round that number up. You keep it as is. So if it's 52, it stays 52. If it's 1 hour, 12 minutes, it stays like this. But if you are calculating your zonal time, because the time zones are not split by minutes and seconds, they are split by even hour. So you have 1, 2, 3, plus or negative. So once you divide the longitude with 15, you keep it as an even round number. So you would round this to 1 and you round this to 1. So that's the first thing that is important to know when you are calculating the time. If you are looking for UT time, exact UT time of a celestial event, you divide your longitude with 15 and you keep the number exactly as it's shown on display. If you are calculating time zone, you round that number up. Now, the way I do this in school, and this is what I do in school, is for this first one, I put longitude divided by 15 in one equation. In the second equation, I put plus minus x. Now these both values are obtained the same way. So longitude divided with 15 is number, and here this is longitude divided with 15, but just one number, just an hour. So if you get this, you automatically got this. You just need to round this value and put it here in the second pattern that you are calculating. But I do know that most of the patterns available online for both calculations, they put its longitude divided with 15 in both parts, and then people get confused. How come those two values are different numbers when it's the same sign? Basically, what that means is here you are looking for your time difference expressed in angle to convert it to time, and here you are looking for time zone, and time zone is economical, so it can only go +1, +2, +3. Only certain countries have quarters like 45 minutes, but they do not have navigational how to say merchant harbors, so they are not important for us. Okay, so we have this, and let's go back to the triangle. So we have this triangle here, and when we are calculating, in order to calculate that triangle, the first thing that we need to know is UT time. So we have two options on a ship. We can have chronometer, or we can have zone time. Chronometer and UT are separated by error. So our ship chronometer clock can have an error. The error is usually plus or minus couple of minutes, and the error is happening because of the shaking and rolling and pitching of the vessel, and mechanism can be tilted a little bit, or certain things can happen to the chronometer. Usually chronometer is placed in the middle of the ship, protected in the box, so it's safe from that. And also this error is checked every day regularly around 12 o'clock by using the noon report. So what you actually have is on MF radio, 2000 and something is the frequency, or today you can also use GPS and of course internet connection. You have a signal transmitting the exact moment of noon for Greenwich, and you check what your chronometer is showing at that moment, and the error between the actual noon and the number that is displayed on your chronometer is your error. So that's chronometer error. Here, if you read the value of observation of celestial object from your ship's local time, so local time, difference to get UT time, because we need UT time to go in the almanac, is your time zone. And this time zone is exactly a number, so it's 1, 2, 3, east or west. If it's east, it's positive. If it's west, is negative. So here there's only one number, even number, from 1 to 12. So 12 time zones negative, 12 time zones positive. So this is how we get time, and this is the first step in calculation. So first step in calculation is to get UT time. We need UT time to enter the almanac. So let me show you a task from the exam. So this is a task from the exam. So on the 14th of January 2008, ship is on assumed position, latitude and longitude. Ship's chronometer error, so this is the value that is going to be given to you in the task, is negative 1 minute 56 seconds. We also have time zone of assumed position, so because it's 141 degrees 50 minutes east divided with 15, that makes 9 hours east, 9 hours positive. And we are observing celestial objects, and look how the time is given. You have either TX or chronometer time. So TX chronometer time, TX chronometer time. So let's look at the first one. First one is Menkar, and I'm going to switch back to camera. And I'm going to type in the numbers. Let's go back to camera. Where's my pen? Here. So TX time of Menkar is 21:16:55, And another star was measured at 12 o'clock 13:10. And keep in mind our longitude is 141 degrees 50 minutes east. So here I have chronometer error. Chronometer error is negative 0.000156. And here I have time zone is +9 because it's east. And if we use calculator for this, so you can also calculate time using the calculator, because 1 degree has 60 minutes and 1 hour has 60 minutes, so the calculator will not go beyond 60 for either degree or hour. It will count up to 60 and then it's going to turn into another hour or turn into another degree. So 12 degrees, calculator is going to know that's an hour. 13 minutes 10 seconds minus 0 hours 1 minute 56 seconds, and that is 12 28 14. Now for this one, 21 16 55 minus positive 9 o'clock, and I get 12 16 55. Now what happened here is I measured these two objects in approximately 10-15 minutes of time in between those two measuring. So the UT time needs to be approximately the same because I'm measuring them approximately at the same time. The reason why these two original numbers are completely off is because this is my local time. So when I'm observing a star, it is actually nighttime. It's sunset. It's 9 o'clock in the afternoon, and chronometer is showing 12 because chronometer is actually UT time with small device error. And the end numbers, if this is one task, the end numbers, UT time 1, UT time 2, all the UT times should be couple of minutes apart. If you get here 12 and here you get 14, 15, then you made a mistake somewhere here, because everything is happening at the same approximate 30 minutes plus or minus, because you go outside, you measure one object, you write down the data. You go outside, you measure another object, you write down the data. Now, if it takes you more than 5, 6, 10 minutes, give or less a minute, that's okay. But these two times, UT time when you observe one star and UT time when you observe the second star, they need to be closer to one another. Okay? And this is important on a written exam. You need to see, is the time given as chronometer time or zonal time, local time. In Croatia, keep in mind, in Croatia, for Croatian students joining in, the TX can also be written as LT, local time. It should be TX. That is a standard mark for everything and everybody in the maritime industry, but they sometimes put LT in the bracket. Now, I hope this part was easy, and now we come to the hard part. The hard part is the date. So, if you have this combination here, and if they tell you blah blah is observing blah blah on 14th of January, TCH, chronometer time 12 o'clock, so you will go into almanac on this hour, on this date. That's easy. But in this situation, let's say it says on 14th of 1st at 21 hours, you are observing this celestial object. This is 12, but are you still on this date? That is important. Local time is 21, 14th of 1st. UT time is 12 because you are east. That means that the date is okay. What would happen if you are actually 141 degrees 15 minutes west? So you are on opposite meridian, so you are west. So it would be Tx is 21, 16, 55. So that's your nighttime sunset. Minus x, and it would be minus 9 degrees, or 9 hours, sorry, because it's west. And UT time would be 21. Minus and minus would give me plus 9, and that would give me 30. So that means I'm 16:55. I actually crossed midnight. So if I'm on 141 degrees 50 minutes west on 14th of January observing something on the sky, I get that UT time is 6 o'clock. At the same, exactly the same moment I have 21, UT has 16:55, but the date is no longer 14, the date is 15, and this is the date I enter into Almanac. So this 6 hours 15 of January, not 14. If the time is given as local, so if the time and date are given to us in the task as local date and time, usually for east longitude, they stay the same. But if the longitude is west, and in most cases is west, that means usually that your local date is the day before and the UT date is the day after, if you cross midnight. Once you calculate the UT. If this value here was still 23:50, it would still be the same date. But because we crossed midnight, UT crossed midnight, it is actually the following date. We are at 14, but the Greenwich is not at 14. Greenwich is at 15. And this is a common and frequent mistake people do on the harbor office exam. So exam for first officer and third officer. So be careful about this. Check the date, especially if the longitude that is given is extremely high and west. So if it's 20, 30 degrees, 50 degrees east or west, that's okay. That's not going to change the value of the time too much. But if you have large longitude and it's west, make sure that you check the date. Is the date correct? Actually, in the exam that was given to the last group, they actually made a mistake. In the exam, they gave the wrong date. They gave 14 and it's supposed to be 13. That is going to be converted into 15 because of the longitude. Is this part clear? Is the timing calculation of UT time clear? Okay. So that's the first thing that we need to calculate, UT time. Second thing that we could do, and the order is not exactly important because the step 2 and step 3 are not depending on one another. So you can do either step 1, 2, 3 or step 1, 3, 2. So 2 and 3, the steps I'm going to show you now are not connected, so it doesn't matter which one you're going to do first. So let's say the next thing you want to do is correct the height, because the height that you actually measured with sextant is not the actual height. It is height measured with sextant, so it's labeled as that. It's height sextant. But because sextant as a device can have, you see, these bolts and everything can become loose if they're not maintained properly. So a sextant as a device can have an error, and some of the errors can be adjusted. For example, this can be adjusted, this can be adjusted, so you can neutralize those errors. But there are some errors, like in this section here or this section here, that are permanent errors by the manufacturer. And let me see, do I have, okay, so this is what I get. So in the box where I have this device, I have this, and this is the inspection results of the product. So the person who inspected this, he told me that when I'm measuring some angles with this device, and if the measured angle is anything close to 10 degrees, the error I need to add to whatever number I read is plus 0.1. If the angle is 70 degrees, I need to subtract minus 0.1 from everything that I actually measured here on this device. So this is Marine Sextant Certificate of Qualification. If Sextant has some permanent errors that cannot be corrected, it will be presented to you in the box of Sextant. So this is a very important document, and it needs to be always, usually it is permanently laminated on the box of the Sextant, and you also have copy inside the box. Okay, and this can be either index error or the centration error, but for purpose of this example, we're going to call this index error, because that is the most frequent error sextants have, if they have errors. So let me put this back. So let's say I measured with this sextant, with this device, I measured height sextant of the sun lower limb. I have two options. So sun is a ball, so I have sun, and I can measure, I can put it on the horizon like this, or I can put it on the horizon like this, so under the horizon. If I do it like this, this is called lower limb, and if I do it like this, this is called upper limb. We do not measure the center of the sun, because that would be guessing. So because the sun is a big ball when you are looking at it through the sextant, so you either lower limb or upper limb. Usually it is lower limb, so standard is to measure the lower limb of the sun. So let's say height of the sun is, let's keep it simple for the first number, let's say it's 40 degrees. And my height of I, so this is me, this is my ship, this is water level, and my I is, let's say, 10 meters. So 10 meters above the water level. So that means actually between the horizon and actually my horizon of the eye, there is this thing here called dip. So that is the first error that we need to take. So we would take almanac. Now this is important. This first, do you see this first section that is white? This is changing throughout the year. So if I have almanac for 2018, this part is valid for 2018. And if I want to use it for 2020 and 2030, I will need to get this part new one, new numbers. But this yellow pages and the pages on the back, they are constant. So even if you have almanac that is 20 years old or 50 years old or for the future, this part will work. You can use this part and it will always be the same. So there are no changes here. This is something that is not changing throughout the year. So you, no matter what almanac you have, you can use this part, this section here. Now the section I'm looking for are these sections here. So they are altitude correction tables for sun. So I have lower limb here and upper limb here. But for the purpose of this video, I also, where are they? I also have them zoomed in. I know you still cannot see it, but at least it's bigger than what you have here in the book. So that's the same table zoomed in. So I have lower limb and upper limb. So I have two tables, and usually they are placed like this on one page or on two pages. So you have lower limb, upper limb. If you measured sun, you are only using one of these two tables. So either this one or this one, not both. So either lower limb or upper limb. So one table. So we measured sun lower limb, so that means we are using this table here. And this is the first correction that we need to take out. We have some numbers here on the left, and we have some numbers here on the top. The numbers on the top are height of eye of observer in meters. And the numbers on the left is height of sun lower limb observed with sextant. So the way to use this table is I have 40 degrees. So from the left, I enter with 40 degrees. And my height of eye is 10 meters. So I look here for number 10. And the correction is 9.4. And everything here is in minutes. So correction number one is plus 0 degrees, 9.4 minutes. So that's first correction for the sun lower limb. I go to the table from the left, from the top, from the left, a sextant height, from the type height of the eye in meters, and I get the value. Now, if you have United States version of this table, it will not be in meters, it will be feet or whatever they're using. So you have to convert the number here and then use it. And if you have a Croatian version of this table, this is going to be written on Croatian, and the table is the same. And this table can be used every time, all the time, 3,000 years in the future and the past, because this number here depends on refraction. Refraction is deviation of your eye when you are looking. So let's say this is Earth and you are here. The sun is actually here, so there is a curvature because of the atmosphere and everything, but it appears to you as the sun is here, and that is called refraction, because you are actually looking at the sun through different density. You have Earth's atmosphere, you have space, and you have everything in the space. So that is why you have this slight distortion between where do you see the sun and where the sun actually is. So all of this, and plus a lot of tiny other corrections that are happening because of the Earth size and the sun size and position, and all of those errors combined were created in this table. Now, for the sun exclusively, we also have additional small error here that depends on the month when you are looking at the sun. So in our case, we are looking at the sun, let's say January. Where's my note? So let's say January. So 1. So we go here, January. Correction, second correction in minutes is 0.3. So plus correction 2 is plus 0 degrees, 0.3 minutes. Okay? So those two corrections are corrections because of the atmosphere, Earth, and because I didn't jump in water. If I jumped in water to measure the sun, I could ignore this. I could not ignore this one because this one depends on the calendar when I jump in water, but I could ignore this correction. So you could save yourself. If you jump in water, you can save yourself from this error. You don't have to read this error out. Now, let's go back to reality. You are here, you are not jumping in water, so you do this number. Because of the month, you do this number, and you also have your device, fancy device, that the manufacturer said has an error. And what was the error for 40 degrees? So for 40 degrees, error is minus 0 degree, 0.1 minute. So if the measured angle with sextant is 40, the error is minus 0.1. What else? Where is the... give me a moment. Now, in 95% of cases, we do not use this table. This table is for temperature and pressure correction. So when you are measuring also with sextant, you also have variations in the atmosphere state of density depending on the temperature and pressure around you, around your position. Usually this error is 0, so that's why we ignore it. But let's see are we going to get 0? So our height is 40 degrees, and let's say, I don't know, do I have a pressure? Pressure is 1000, so 1000 is the pressure. And what's the temperature now? Temperature is, give me a temperature, come on, weather station, 20 degrees, summer. Can you believe 5 days ago it was -7? Oh, this is crazy. Armageddon. So 20 degrees Celsius, and this is HPA. That's the pressure. So my height is 40 degrees. I have this column here. So for heights between 10, 12, I enter here. 13, 15, I enter here. 16, 20, I enter here. In my case, the height is 40, so that's the last column or first column. 34 to 65, so that's the first column I enter. And then from the left, I enter with temperature. Temperature is 20, and the error so plus temperature, error is 0. And let's put pressure, so we stay in this column. Pressure is 1000, and it's 0. So this is what I said. Usually we skip even looking at this table because for most of the values the error is 0. But if in the exam they're asking you to get temperature and pressure correction, you come here, you go on the top from the height, you look for the height. Once you find your column for your height, from the left you enter with temperature, and from the left you enter with pressure. So 2 corrections, 1 correction for temperature, 1 correction for pressure. Now, if you have Croatian almanac, this tab is little different. This tab is little different, but I already have a video about that. And because this is on English candidates are not going to use Croatian almanac, so they will have this. So if you are going on the master exam, celestial navigation, you will need to know this part from Croatian almanac. You can make a comment or write me an email, and I will make special video for that Croatian table. But even if you are doing the exam on Croatian language, you can still use this table because the result from here and Croatian table are the same. So they have to be the same because this is a table that doesn't change throughout the year. This is just how much the fraction between the atmosphere, depending on different temperature and pressure, is happening in the atmosphere itself. So that's the refraction. Okay, and now that we have all this, it's just pure mathematics. We need to, so 40, it's not going to go over 40, so I can, and this is height through. So after I add all these corrections, the height we're going to get is actually height through. No, in Croatian almanac, let me see, where's my almanac? If I can find it quickly. Croatia, where are you, Croatia? Croatia. Almanac, Hrvatski almanac, give me a second. Yeah, it's, no, that's not it. Jenny, Hrvatski almanac. Admiralty. Nema. Sorry. Stipe, I have somewhere in this mess of my office, I buried somewhere Croatian almanac. Let me see, it's here. No, it's somewhere around here. I don't use it because I have my own, but it's somewhere in here. Once I find it, I will show it to you later on, or I will make a new video about it. It's not the same as this one. It's not the same. The top of the table is different. So once I locate my Croatian almanac, I only have one, unfortunately, Croatian almanac, and because I do not use it often, it's somewhere around here, but I do not see it. Okay, that later. I will show you that later once I track that down. Let's move on. Where were we? So 40 degrees, but the number is going to be the same. So if you have Croatian, Chinese, Russian, United States, UK almanac, for the table correction part, if you get table from here, from here, from here, from here, every number is going to be the same. The way you obtain the number is different because every table has slight differences how you enter the table, but the end number needs to be the same. So if this almanac gave me 9.4, this one and this one and this one and this one, they all need to give you 9.4 as a result. Oh, wait. Oh, be smart, Marina. Be smart, Marina. I have it here in my book. So if you have this book, Stipe, if you have this book, come on, Celestial Navigation. Here. Yeah, baby, Celestial Navigation. So if you have my book for masters and officers for the exam, on the page 62, you have explanation how to use the table for temperature and pressure Croatian version. So this section is the same. The only difference is they have this part different from my almanac. So you have it here, you have instructions here in the book. If you have the second one, the 1 and 3, so the second one for masters, this one is for officers. If you have for the masters, it's the same image, same picture. It's under Celestial Navigation, so it should be in the beginning where you have these triangles and everything. So you see calculator and as well, and the celestial spheres and everything. So you have it here. Okay, let's go back to this one. So we have 4 plus 3 is 7, minus 1 is 6, 9, and everything is 0. So height true is 40 degrees, 9.6. Now I did this by hands. If you don't want to risk it, do it with calculator so you are safe. So 14 degrees plus 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 minus minus, and this is height true. So this is the actual height. So this is the actual height of the sun lower limb. If I jumped in water, I would skip this. If there is no month correction for the sun because of the tilt of the earth and everything that's happening, I would skip this. If there is no error of my sextant and temperature and pressure, the height observed would be the same as true. But because of all of this, we need to do the corrections. Let me just take... Sorry. Okay. So this is the procedure to correct height of the sun. If the task was height of sun upper limb, everything would be the same, except instead of this table, I would use this table. And if you can see here, if I zoom in, I don't know, I turn the autofocus off. So all the values for upper limb are negative. So you have in here, only this one is negative, only these values are negative, everything else is positive. For sun upper limb, everything is negative. All the values are negative. So for this first correction, it will be either this table or this table. So not both of them, so either this one or this one. And that is how you correct the height of the sun. What if you observed star? So height of sextant of a star. And let's say it's 25 degrees. And let's say height of eye is 18 meters. And let's say month is July. Now, this is a table, altitude correction table for stars and planets. So stars and planets. Once again on the top we have height of eye of observer in meters, and we have height of star or planet observed with sextant. That is what we have here. We take ruler or something, and we look for 25 and 18. And 25 and 18 gives us minus 9.6. So the first correction plus correction is minus 0 degrees 9.6. And this is the dip error. Now, second correction for stars doesn't exist. So that's it. For the stars, that's it. We have device error, so index error. And if it's 25, so I have for 20 I have 0, for 30 I have minus 0.1. So technically, if I want to be precise, I should split this on half. So that would be 0.05. So if it's 0.1, half is 0.05 and 0.05 when I split this in half. Because I have 25, I need to interpolate the middle between these two values. One value is 0, the second value is 0.1. The middle between those two numbers is 0.05. Okay? So that's index error. If I had pressure and temperature, so 25 is here between 22 and 33, so that's this column. Temperature is 20, so I have correction for temperature. So for temperature is minus 0 degree, 0.1. And for pressure, 1000. So for pressure, oh, look at my fine writing skills, is 0. And that's it. Height, true. So the difference between sun and star is obviously using different tables. Sun has its own table, stars have their own table, but the correction number 2 for month, calendar month, doesn't exist, so you don't have that one. You only have this one. And usually for the star and planets, the correction is always negative. For the sun, it's either positive or negative, depending are you measuring lower or upper lip. And here we have 25 degrees minus 0 degree 9.6 minutes minus 0 degree 0.05 minutes and minus 0 degree 0.1 minute is 24 degrees 50 what is 50.2 50.16 divided, no, it's 15 divided by 6 is almost 3, so 15.3. So height true of the star, corrected, the actual height, is 24 degrees 50.3 minutes. So that is how you get height of sextant of the star to true. What if you observed planets? Now for planets, everything would be the same if the planet was Jupiter and Saturn. If you observed Mars and Venus, you have additional small, just like for the sun, you have small correction here for Mars and Venus. Now for Venus, you have two options. If you observed Venus anytime during the year except December, the correction is 0.1 plus. And if you observed Venus during December, the correction is 0.2. And if you observed Mars anytime, whenever, whatever, the correction is 0.1. So if this was Venus anytime except December, it would be plus 0.1 additionally. If it was December, plus 0.2, so Venus. And if it was Mars, plus 0.1 always, all the time, that's extra correction for Mars. And Jupiter and Saturn, they are exactly the same, nothing has changed. So star and two planets, Saturn and Jupiter, they stay the same, the correction stays the same. Only Venus and Mars have special, these tiny corrections here on the bottom. That's it. We have moon. Okay, moon is moon. Let's see, moon. Okay. Moon has its own specific tables. It has this table here for the dip, and you enter, you see the mark here, you enter with your height of I to get the first correction for the moon, but the second correction for the moon, this one here, you enter with HP. HP is horizontal parallax. So if you take any page here on the hour that you measured the moon, height of moon, you will also have this value, last column, that has HP. So HP is 61. So you go here, HP is 61, and from the left you have height. You measured with sextant, and this is the correction for the moon. So the top, you enter the column or table for altitude correction tables for moon with horizontal parallax, and horizontal parallax is the value that you read from here depending on the UT time. So UT time of observation, you get HP here, you enter here, here is the height observed with sextant, and when they intersect, that's the correction for the moon. So sun has its own unique tables, star and planets have their own unique tables, and moon has his own unique tables for height correction. The temperature and pressure correction are the same for everything. So this table here is exclusive. So this is for sextant altitudes, no matter what you measured, either sun, moon, star, or planets. This is the correction for temperature and pressure, regardless of the object. So is this part clear? Is the part how you correct the height clear? How you get from what you measured, how do you get to true? I dropped the papers. Okay. Thank you, Matthew. So step number one was we needed UT. Step number two, we need to have height true. That's the actual height of the observed object. Step number three is to get local hour angle of that object. So what that means is Greenwich is here, object is somewhere on the sky. This is his Greenwich hour angle of the star, and this is where I am. And in order to calculate anything, I need to know local hour angle. I need to know how far is this star from me. Not in reality, this is all imaginary. So I have myself, if you remember from yesterday, I have my meridian on Earth, on globe, transferred on this imaginary globe surrounding the Earth, and I have a star somewhere in the space transferred on that same globe but on the outside, and I have this imaginary distance between me and him or me and her, and that is local hour angle. So my meridian is drawn here, her meridian is drawn here, and I get approximately space-wise, this is our angle, local hour angle. Now my distance between me and Greenwich is my longitude. So in order to get local hour angle between me and the star, I need to have my longitude, and I need to know Greenwich hour angle of the object. Longitude is from my assumed position. So everything that I'm going to calculate now is me closing my eyes and I say, oh, I'm here. And now I take latitude and longitude of that position. But with my sextant, I actually measured true value. Now I'm calculating what would be the values of this same star if I'm here or somewhere on the globe. So that means I have my longitude, and I'm going to use the longitude from the task. And the longitude from the task is 141 degrees 50 minutes east. The date is 14th of January, and the star was Menkar. So that's the name of the star. And the time of Menkar, TX, was, I have it somewhere here. So TX was 21:16:55, and I calculated that in the step number 1 to be 12:16:55. So that's my UT time. That is what I need to calculate local hour angle. Now, what is the procedure to get local hour angle of the star? So the first thing I need is Greenwich hour angle of the star. I cannot have that because, remember from yesterday, this is Earth, so tiny little dot, and then we have a star here, our sun, and then we have a star somewhere in the space, and it is very hard to calculate distance between our Greenwich and the star very far in the space. So what we have actually is Greenwich hour angle of Aries. It is expressed with the Greek letter gamma in the index. So this is spring point. And in almanac, we're going to get this value for exact hour of UT time. And then we're going to have correction for minutes and seconds of our observation time. And these two is going to give us Greenwich hour angle of Aries. So how far is sun frozen in first moment of spring on this hour, this date, and minute and second. Now on this value, I'm going to add sidereal hour angle of this specific star. So this is the value how much the star is away from the frozen sun position at the first moment of spring. So once I add these two values up, I would get how far is the star from Greenwich. And on this value, all I have to do is add my longitude. And once I add my longitude, that can be either positive or negative, I will get local hour angle of the star. I will get how far is the star from me. Now, this step here can be skipped. If this is high school, we would do everything step by step so people can practice. But in reality, because we want to save time, the procedure goes Greenwich hour angle of Aries plus correction plus sidereal hour angle of the star plus longitude, and all together gives me LHA of the star. So I do not need to summarize each individual step. I get 4 numbers, I summarize 4 numbers, and I get the result. The result is an angle, and can be only between 0 to 360 degrees. If I get the value negative, I need to add 360. If I get the value above 360, I need to subtract 360. Just like azimuth. If I get azimuth of minus 2 degrees, that's not possible. Azimuth cannot be negative, or course cannot be negative, so it's actually 358. Okay, so high school, do this faster. Something that you would do on ship is you have 4 numbers, you get the final number, because on ship this is the number that we need. In high school, to get more points, they want you to do all these numbers in between. So let's do this. I need Greenwich hour angle of RES, spring point, on this date, on this time. And get me almanac. So I open almanac. Very important, find the correct date. So 14th of January. And I'm not done yet. I didn't find the exact date. I just find the page with the exact date. So I still have 3 options to make mistake. I can take 13, 14, and 15. So I need to take 14. So the first block here is 13, second block is 14, the third block is 15. I need 14. So 14 is in the middle. I have 2 sides. One is for stars and planets, second one is for sun and moon. I'm observing the stars, so this one is ignored. And I'm looking for RES, and RES at 14 of January, and the time is 12. So I'm not looking at minutes and seconds at this time. I'm just looking at 12. And 12 o'clock is, let's move it aside. So it's 293 degrees, 20.3 minutes. Greenwich hour angle of RES 14 of January at 12 o'clock. Now, in reality on ship, I would not do this step now, because this step requires for me to turn pages in front. I would skip this step and I would go here because this value is on the same page. So I'm looking for the name of the star, and the name of the star is Menkar. Under the name Menkar, I have sidereal hour angle of the star, and it is 340 degrees, 19.2 minutes. Now, at this moment, I do not need to know how far is this star from the equator. I do not need to know declination. But because I'm here and I want to save time, I pick a place somewhere on my paper that would be nicer than this one because I'm using this. Usually I use technical pen, but never mind. Declination is 4 degrees, 7.4 minutes north. Now, I do not need this number right now, but I will need it in the future. So once I'm here, I write it down. So this page is finished. I don't need to go back on this page ever again for this task. Now I look for correction. Correction is in the yellow pages on the back. And for the yellow pages, let me see, do I have them? Give me a second. I should have them zoomed in, zoomed in, zoomed in. Height. Come on, I just need one. No, sorry. I hoped I have one of these zoomed in, but I do not have them zoomed in. So let's do it like this. So you have these yellow pages covering every minute. Every page has 2 minutes. And every minute has 2 tables for herself for the 32-minute correction. This first table here is for correction of hour angle, and the second table is for correction of declination. So 32 minutes, and then you have one table, second table belonging to 32 minutes. Then you have a next minute, one table, second table belonging to 33 minutes. If you have United States almanac or UK almanac, these 2 tables are not physically apart. The only way they are separated is by they have a bolded line in the middle. So that can be quite confusing because people connect them. They believe this is all just one table. No, this is one table, this is second table, but they both belong to this minute here. Okay? So I'm looking for 16 minutes. So that means I have everything here from 0. So it starts obviously with 0, increments and correction tables. So it starts from 0 all the way up to 60 or 59. And I'm looking for 16. Here it is, 16. And under 16, I need to find 55 second. 55th second is here. And I have three options. First column, second column, third column. First column is hour angle correction if I observed sun or planets. If I observed stars, that means I'm using Aries, I'm using spring point, I'm using the second column. And if I observed moon, I'm using the third column. In my case, I observed star, so that means I'm looking for hour angle correction for Aries, and that means second column. So 55 seconds at 16 minutes makes it 4 degrees. 4 degrees, 14.5 minutes. What is this value? This value is actually telling me how much Earth moved, tilted, in these 16 minutes and 0 to 60 seconds. So for example, if you can follow right now, I said that Earth shifts 15 degrees in 1 hour. Okay, so 1 hour 15 degrees, 1 hour 15 degrees, 1 hour 15 degrees. So that means 1 hour 15 degrees. How many degrees the Earth is going to move in 30 minutes? I'm guessing you know the answer, but let's say you have no idea about anything and you don't know how to divide 15 by 2. How would you solve that? So what is half hour? Half hour is 30 minutes, 0 seconds. So you go here, you look for 30 minutes, see 30 minutes, 0 seconds, and you see here on the top, the sun or planets or everybody on the sky moved by 7 degrees and 30 minutes. So that is 7.5. And that is how you get correction. So Earth moves in 1 hour 15, in 30 minutes and 0 seconds, it moves 7 degrees and 30 minutes. This is just extrapolation of all those results. So if you divide 15 with 29, this is the result. With 31, this is the result. So this is a table in case you do not know how to divide with 15. Or to make it easy so you don't have to calculate, just come here and do the numbers. You can also do this by calculator, so you don't have to actually use this table. You can use calculator, but if you have table and if you want to avoid too much calculations on calculator, you can use this table. So once again, you enter here by finding the correct minute. Once you find the correct minute, you have all the 60 seconds on the side. You find the correct second and then either sun or planets, Aries or moon. If you observed star, that means you enter under Aries column. Okay? And the longitude of assumed position is the number that we decide. It's going to be 140 degrees, 15 minutes east. Now, this plus this gives me this. This plus this gives me this. This plus this gives me this. Now, I can put it here, but for the sake of this lecture, I'm going to do it here. So 293, 20.3 plus 4 degrees, 14.5 is 297, 34.8 plus 340 degrees, 19.2. I have 611.54. Now, if this was the end of the task, I would need to subtract this by 360 because it's over 360. But because this is not the end of the task, I'm not going to touch it right now because this number is not important. This number is important. So I'm just going to continue. Plus, because it's east, if it was west, it would be negative, plus 141 degrees, 15 minutes. And I get 753 degrees 44 minutes exactly is local hour angle. Now it can be only between 0 to 360, so what I need to do is subtract 360. Still 393. What do I do? Never mind, just go one more time, minus 360. You just go minus 360 until you get the number that is between these two values. So that means local hour angle is actually 33 degrees 44 minutes. That's the value of local hour angle. That is how far star is from our meridian on the celestial sphere. Now, this number is also important when it comes to rules. On celestial sphere, we have north. And we have this star. That is local hour angle. And local hour angle is measured when the Greenwich shifts in this direction, towards this direction. So it's this star is 33 degrees away from Greenwich meridian on this side. So the Earth is rotating and everything is moving in this direction. So star is here. This is 30 degrees local hour angle. What this means is that the bearing of this star is going to be over 180. So it's going to be over 180. So if LHA is between 0 to 180, that automatically means that the bearing of the object is going to be between 180 and 360. That's the rule. Because azimuth is measured over the point of east in a clockwise direction, while local hour angle is measured from Greenwich meridian counterclockwise over the side of west, because everything on the sky is moving towards west. So it's going, the celestial sphere is shifting from east towards west. And because of that, because they are being measured in different direction, if local hour angle is under 180, azimuth must be over 180. So by getting this number under 180, I automatically know that the number I'm going to get, the azimuth, has to be between these two values. I cannot have local hour angle between 0 and 180 and azimuth between 0 and 180. It's not possible. So if the star is here, the bearing would be 160, azimuth would be 160, but the local hour angle would be over 180 because it's measured from here in counterclockwise direction. So it's not possible for a star to have local hour angle small and azimuth small. I hope that is clear from the image. Blink twice if you've been held hostage. And let's move on. I hope this is clear how you get local hour angle of the star. I will continue with who's panicking. Give me a moment. My daughter is sending something. Okay, and as you know, she is priority number 1. So, sorry. I'm a taxi driver, so when she snaps, I come. So, okay. But she doesn't need me. She's just telling me when to come. We are safe. We still have 2 more hours. Yay. Okay, so this was local hour angle if you observed star. Now, because we are still on this step 3, and as you can see here, the step for height has nothing to do with this. So if you want to do local hour angle first, not the height, it doesn't matter. So you can either do height or local hour angle. These two steps can turn, but the number 1 has to be UT, because you cannot calculate local hour angle without knowing the exact UT. So number 1 is always get the correct UT time, and then you can either do height or local hour angle, doesn't matter which one, but you have to do this one and this one. And the step number 3, as I showed you the step number 2 for everything, I'm now going to show you local hour angle for everything. So this was for the star. How would this procedure look different if you are observing sun? So for sun, okay, thank you. So Greenwich hour angle of the sun, and let's keep it lower limb because never you're going to observe upper limb. So Greenwich hour angle of the sun, and let's keep everything the same. So it's 14th of January. So 14th of January, once again, the rule is the same. I remember I told you this is one page. The page has left side, right side. I'm looking for SUN, Sierra Uniform November, sun. So don't make a mistake, look for the sun. 1, 2, 3 blocks. I need block that belongs to 14. So 14, and let's use the same number, so 12. 14, 12. Greenwich hour angle of the sun is 357 degrees, 46.7 minutes. I do not need declination of the sun. I do not need declination of the sun for LHA, but just for the sake of this one, I'm going to write it down. It's 21 degrees, 21.8 minutes south. Now, I will explain to you once I'm finished with local hour angle, what do we do with declination. Practically, these two calculations can be done right now at the same time. Usually I would not do them separately, but for the purpose of this tutorial, I'm going to split them. It's easier if you do them simultaneously because all the numbers are here on this page. So that's it, what I need from this page, Greenwich hour angle and declination for 12 o'clock. Now the second step is correction for 16 minutes and 55 seconds. And now, because of the sun, I'm looking at the column of the sun. So that's the first column. So that is 4:13.7. 4 degrees, 13.7. For the planets, it was 14.5. For sun is 13.7. And that's it, plus longitude. And longitude is 14150 east, LHA of the sun. So 357, 46.7 plus 4 degrees, 13.7 plus 14150, and I get a big number, 503, 50.4 minus 360, it's 143, 50.4. So that is local hour angle of the sun lower limb, and that's it. So sun doesn't have sidereal hour angle because that's the sun. Sun, how far is the sun from the sun? 0. So that's it. Correction for minutes and seconds of the UT time, and a longitude to get local hour angle of the sun. That's the end of local hour angle, step number 3 for the sun. What if we were observing planet? And let's say that planet is Venus. So Venus, the procedure for Venus. Once again, we have 14th of January. We have Venus at 12 o'clock. And it's, don't worry, I didn't forget about declination. The procedure for planets and sun for declination is the same, so I'm going to talk about that. I'm going to do them later. So Venus is at 36 degrees, 17.3. And now we have something special for planets that nobody else have except planets and moon. So only planets and moon have this. On the bottom of the column for Greenwich hour angle of each planet, you have V value, so tiny little V value that can be either positive or negative. For every planet is usually positive except for Venus. For Venus is sometimes negative. So V value on the bottom of the column is 0.8. Now, the way you plot that number here is plus V equals minus 0.8 and you close the bracket. So this is not the correction. This is coefficient that you are using to get the correction. So this is not the correction. You put it here on the left and you will use this number to get correction. Now, what is this number? This number is a variable of change between each hour for the planet, because planets are not moving uniquely throughout the time in 365 days. So they are shifting slightly. There's a slight difference, and that difference was compressed into this coefficient. And for every 3 days you have this coefficient, and by using this coefficient and the time, minutes and seconds, you get the slight correction of the V value for this planet. So that is extra correction nobody else have. Only planets and moon have this special unique correction. So sun doesn't have it, stars don't have it. So the next correction is for correction for minutes. And let's find these two corrections. So you go on the back and we are looking for 16 minutes. 16 minutes. So 16 minutes. And now because of Venus, we look at the sun and planets. So that means this correction is going to be the same. 4 degrees, 13.7 minutes, because the column for sun and planets is the same. How do I get this correction? Remember I told you this minute, every minute has two columns. First column is for correction of hour angle. Second correction is declination correction and additional angle correction for planets and moon. And you enter this table with V or D. So either V value for hour angle or D value that is also on the bottom of the column for declination. So in our case, we have V value that is negative, so that means the correction is also going to be negative, and it's 0.8. And for 0.8 under 16 minutes, correction is 0.2 minutes. So that is how you extract the V correction value. You enter the column with V value, ignore the seconds, so seconds are not important. This column is for 16 minutes, and 0.8 correction is 0.2. Okay, Matthew, you can continue to watch this later on. The video will be live on my YouTube channel. Thank you for staying here. Thank you for listening. Have a nice day. And we'll see you or hear you or whatever tomorrow morning at 10 if you can. If you cannot, once again, I'm doing this as a recording, and tomorrow we will continue with calculations. This is going to be over soon. The only thing I have to explain is declination, so you can watch that in the afternoon when you have time. Okay, so remember, first one is you enter with seconds. It's for hour angle. The second one is for V or D. The seconds are not important for the second correction. And one more thing, longitude. So longitude 141.50 east. And now you add this up and you get local hour angle of planet. And that is how you solve the local hour angle step. The fourth step, so step number 4, is declination. So if you have declination for the star, you just read it from the table. Declination for the star doesn't change in period of 3 days, so you can have this number and use it for calculation. If you observe a sun or planet, so you have declination of planet. Let's see how do we get that. So once again, we go to January 14. We find the planet, we find declination, and now on the bottom of the column, for declination, you have the d value. If the d value is 0, you don't have to look for the correction, because no matter what minute it is, every correction for d0 is 0. But if d is not 0, in this case, you see for Venus is 0.4, that means we need to say plus d equals 0.4, and we need to read the correction. But now, for declination, we have a specific warning. D value is always positive here. Are you going to add or subtract correction depends on what is happening to declination in this month, in this day. So to get, is the correction going to be south or north, we need to see what is happening to declination of the planet or the sun or whatever we're reading. So we have declination of the sun. So we have declination of the sun. This was sun, yes, so this was sun, d is 0.4, and on 14 the declination was 21 degrees 21.8 south. Okay, so 21 degree 21.8 south. We look what is happening to declination in the next hour. So 21.3, 20.9, 20.5. So that means declination is moving, the sun is moving towards the equator, towards the north. So the correction, we do not know the value of correction yet, but we do know now that the correction must be north. So because sun is moving towards the equator, moving towards the north, the correction that we need to apply to this value, because this value is for 12.0000, we need the value of declination for 12.1655. So that is in the future, and we see here that in the future sun is moving towards the equator, it's moving towards the north, so the correction is north. We don't know what it is, but it is going to be north. So we go to our minute, 16 minute, d value is 0.4, correction is 0.1. And because the correction is 0.1, declination, the actual declination of the sun is 21 degrees 21.7 south. So sun is still under the equator south, but just 0.1 minute less, because it's moving towards the equator, it's getting closer to the equator. And that is how you correct declination for the sun, for the planets, and for the moon. For the star, you have direct value of declination. There is no need for correction. So is this clear? Matthew is gone, so Ivan is also, or John, sorry, John is also listening. He cannot type the comment, but he's listening and sending messages on email, so he's safe as well. So I have Ivan, I have Stipe here, and I don't know, is Red Dragon here as well? So is this clear to you guys? Okay, Matthew. So I'm finishing the lecture for today. So what we talked about today is how to get UT time, 2 options, how to get height true, and the tables to get height true, how to get local hour angle depending on each different celestial object, and how to correct declination in case it's sun or planets. For stars, there is no correction. Declination is directly from the almanac. So these are the 4 steps I wanted to cover today. I covered them, and tomorrow we continue to step number 5. Okay, so if everything is here, tomorrow we go to step number 5. Step number 5 is going to be to get height calculated, and step number 6 to get azimuth calculated. So those two values calculated for an object for any position on planet, and then comparing these two values with the values that we actually get measured with sextant. So that is for tomorrow, how to get height calculated and azimuth calculated. And after we get these two values, the final step, and that's the end of the task, is plotting on the Y chart. So these 3 steps are tomorrow morning 10 o'clock. Perfect. So if you have questions, send them on email or send me on Viber or Viber or however you call that purple thing that you have on your phone. I will see you tomorrow. I will talk to you tomorrow at 10 o'clock, and have a nice day, everybody. Stay safe, and that was it for today. If you want the links for the animations, send me an email, say, Marina, I need those animations, and I will reply to you with the links so you can download them. Okay?